Hello, everybody. Good afternoon. I would like to warmly welcome here at this PHIDIAS webinar. My name is Francesco Zimanti. I'm a digital marketer and I'm a project manager for Trust IT Services. And specifically here today, I'm here as in my role of an outreach specialist for the dissemination and communication of the PHIDIAS initiative. Well, my role in this webinar today is just an introductory role. So before leaving the floor to our esteemed speakers, I would like to give you a broader overview of the context that we are going to tackle today. I'm pretty sure that if you are here today, you are already very well familiar with what the PHIDIAS itself is. But I would like you to give you some ins and outs of the project itself. As you may know, PHIDIAS is a project funded under INEA, the INEA framework, and specifically under the CEF umbrella, the Connecting and European Facility. One of the main goals of PHIDIAS is the realization of a set of HPC tools. First and foremost, to create a sustainable HPC data-powered services, both for Earth, atmosphere, and marine observation for researchers, to make the life of researcher easier and more affordable. At the same time, PHIDIAS wants also to ensure open access to standardized HPC services for the scientific community. And finally, the improvement of the fairization process on the whole. When we talk about PHIDIAS, we are talking about a consortium of 13 different partners that are located in 5 different European countries. And the whole consortium is led by CNES, the French National Computing Center for Higher Education. In the pursuit of these objectives, we are set up a series of webinars this year. We started in February with a general webinar on the overall initiative, and then we decided to focus more on the 3 use cases that that PHIDIAS scientists and researchers are trying to put in place in the context of the project itself. The 3 use cases are dedicated to the ocean data, the big data Earth observation, and the intelligent screening of satellite data. That is actually the subject we are going to be tackling with this webinar today. As you can see in here, these webinars are completely and freely available on a PHIDIAS website. And we are going to be organizing a third one on the last use cases missing in the next December. Before leaving the floor to my colleagues and to the speakers, I would like to remind you a couple of rules that might come handy during the webinar. You have the opportunity, the chances to do some questions to the speakers. I would recommend you to use the drop a message in the Q&A box at the very bottom of your screen, and do not use the chat. Using the Q&A box will facilitate the speakers in getting back to you in a more efficient way. And every now and then I will interact with you in the chat instead, and suggesting you some deliverables and some nice items about PHIDIAS that you can sift through after the webinar. So you can see in this slide in here the remarkable squad of speakers that we are featuring today. We have Pascal Prunet from Spacia. It is specifically dedicated to the development of the use case of the intelligent screening satellite data. We have Nicolas Pascal from ICARE. We have Dominique Jolivet from HyGeos, and we have a guest of honor, Xavier Espinal from CERN, and in charge of the ESCAPE project. He's going to be talking to us about the European Science Cluster of Astronomy and Particle Physics. So, said this, you can find here some contact that you can get in touch with, both with me as a work package leader on the communication services of PHIDIAS, or with a PHIDIAS consortium on the whole. I'm done with my introductory role in here, and I'm pleased to leave the floor to the first speakers. That is going to be Pascal. if you are ready, Pascal, I'm going to leave the floor to you. You can
Yes,
share your
thank you, Francesco.
screen whenever you want, and you can start your presentation.
If you correctly see my slides.
It is now in full screen mode, and yeah, you can go on.
Okay.
Thank you.
Thank you, Francesco. Good afternoon, everyone, and thank you to participate to that webinar. So I would like just to give a sort of introduction about the objective of that WP within PHIDIAS, that is this use case, which is dedicated to atmospheric concern. And the objective is really to progress in detection and identification of atmospheric events. I will say a little bit of word about that, using space data. And this is the main effort. And you will see that for that work package, we are several partners. Spacia is working together with IRIS and ICAR, French data center, together with IPSL scientific teams, and together also with IGEOS company and SRON, Netherlands Institute for Space Research. So just a few words about the context, the well-known context. As you're perfectly aware of, we have faced to Earth and environment challenges at all scale, local, regional, and global scale, with strong impact, expected impact on environment, on Earth, and on economy, of course. And faced to that challenges, there is a lot of effort, of course, and at European scale, there is some tentative answer by developing way to observe and measure and monitor all the events. And we are at a moment at Europe scale that we entering in the area of operational measurement of the air composition from space. Up to now, we used to observe the atmospheric composition. We use and we develop scientific space-based observation with instruments, etc. And now with the initiative of Copernicus and Sentinel, and in particular Sentinel-4 and Sentinel-5, we will have access to operational, high quality, already available observation from space. Basically, we will have the opportunity to use 4 operational atmospheric sounding instruments, Sentinel-4 and Sentinel-5. I will give detail in the next slide. Together with Copernicus service able to use that information and provide forecast analysis of the atmosphere composition and the climate, and also some ongoing effort in order to address specifically the issue of monitoring human emission of greenhouse gases, which is also an effort which could bring information from space. So based on that, there is associated challenge to that. We will have available a lot of information, a lot of data from space. This will be several terabytes each day provided by space mission, provided from polar orbiting satellite, each day's measurement each day over the globe, also provided by geostationary satellite, which will provide each 1 hour, each 30 minutes over Europe, a lot of information about the atmospheric composition. So the question is how to comprehensively deal with all this available information. Of course, this is a very big and global challenge, and we would like to contribute at our scale to that question by providing some capacity of intelligent screening of large amount of satellite data in order to be able to target scene or events, atmospheric events of interest, in order to be focused on and dedicated and used in a dedicated study by scientists or by operational users. This is the goal of PHIDIAS, at least of this use case of PHIDIAS for atmospheric observation from space. So just to give a brief overview of what we expect in terms of added value in the context of a lot of already done work in order to well use that information from space. PHIDIAS could be a sort of third way or alternative way in the middle of operational use of the observation from space, which is already efficient and well in place, based, for example, on the CAMS service, the Copernicus Atmospheric Monitoring Service, which is able to use and assimilate operationally within forecasting systems the space-based information. But this way of use the data have to be operational and efficient. And of course, there is some limitation when you have extreme data related, for example, to extreme events, which is not well used by the operational system. On the other side, the researcher work on that specific case, of course, but there is a lot of data, and they need to have some objective way to focus on the correct data and make screening and make a selection of the data. And so the goal of PHIDIAS is to propose such detection and filtering based on intelligent screening in order to select the useful data oriented to the extreme event. The goal is, of course, probably to be able to develop dedicated services, but this should provide also added value to the operational use and scientific use of the data. How we could do that? The idea is to address two ways of using that information. First of all, we propose to use level one data, that is spectra, provided by Earth observation, and we will focus our work on Sentinel 5 precursor, which is already flying and providing a lot of useful data. So based on the level one spectral data, we propose to make some principal component analysis of the data in order to select the information related to extreme event. I will give some detail about that. And on the other side, we propose also to use directly level 2 product, that is image of atmospheric content of gases, for example, NO2, methane, carbon monoxide, in order to make some selection of the event by detecting automatically the plume and sources of pollution directly from the image. The idea is to propose that sort of automatic processing of the data in order to select useful information to be used by the scientist or more by dedicated services. So we propose in that work to focus on Sentinel 5P data, as I said. Just a few, one or two slides about that data. This instrument provides a lot of information from spectral measurement. This is hyperspectral measurement from the UV spectral domain up to the shortwave infrared spectral domain, with a lot of data every year, basically about a terabyte of spectra each day. So this information is processing by ESA in order to provide level 2 information, that is atmospheric gases information about a lot of interesting species for air quality and for climate, methane and other things like that, NO2, etc., CO. And this is provided in globally each day at a resolution which is very good from space, that is a few kilometers the size of the pixel. So from that two way to process the data, that is principal component basis from level 1 and automatic detection of plumes from level 2. We are developing that two processing in order to be able to provide that operationally at the end of the PHIDIAS project. Few example, just an illustration of the principle of what we would do from the level 1 spectra. The idea is really to use principal component basis in order to decompose the spectra provided by the measurement in order to reconstruct the spectra based on the normal behavior of the atmosphere. And so this is an example of work already done with YASI, a thermal infrared sounder already flying on METOP. With that sort of processing in the nominal case, that is when there is no extreme event, we are able to decompose and reconstruct the spectrum on a specific normal basis. But when there is a specific extreme event, the outlier or the specific signature of the extreme event is not reconstructed by the processing, and we can identify outlier and make maps of this sort of extreme event. And this allows, by analysis of the spectral structure of the outlier, to interpret the information in order to classify in specific extreme events like volcano, fires, pollution episode, etc. So this work is in progress. This is based, as I just said, to already validated processing of YASI data. This is a work developed with the Space French Agency, CNES. Based on that, we are adapting this processing on Sentinel-5 precursors data, and we are on the way to start the first processing of the data. The idea is to test this on few data set of Sentinel-5P, and the goal would be within that project to process at least 1 year of global Sentinel-5P data in order to be able to analyze the added value of such a processing and to put that available to the users. The other way to work is really to start from the image from level 2 product from Sentinel-5P. In that case, the idea is to develop specific techniques to have an automatic detection of plumes and source of pollution. This is based on specific artificial intelligence method, and we are on the way to prepare the processing on the image. We already have used the data in order to understand the data, Sentinel-5P data, on NO2 product, and we are developing the processing in order, again, to demonstrate the interest of such a processing and provided that to scientific users in order to demonstrate also the usefulness of that. Just an example of that second way to use the data. This is a work, what we call a side work, that is something which has been done by preparing the Sentinel-5P NO2 product for the use in PHIDIAS. We take the opportunity of accessing to this data to have a look to the pollution level over some city over Europe in 2019 compared to 2020 during the COVID period, in order just to see if the Sentinel-5P NO2 product is able to see something. Of course, this is a complicated exercise, but this is very interesting and very powerful, and this allows to show that we are able to map the pollution level, if we are speaking about NO2 pollution level, map the pollution level over some cities, and look at the difference between the years, as well as looking at the temporal signal of such a pollution level. This is very interesting in terms of result from Sentinel-5P, but for PHIDIAS, this allows us to start dealing with the data, understand better the information, and prepare the use correctly of Sentinel-5P. Just to finalize this introduction, I would like to insist on the fact that the space-based Earth observation will provide and already provide a lot of data with complex informative information. And so the real challenge is how to extract that comprehensively. We know that operational models are ready to use that, of course, operationally, but there is some missing aspect related to extreme data, and we have to prepare that use objectively for the scientists. And PHIDIAS is really a tentative to deal with such a challenge and propose approach to perform a better and more efficient use of the data. So I would like to thank you for the attention and give the floor to the next speaker.
Yeah, I take back the floor, shifting to Nicolas Pascal. Thank you very much. In the meantime, Pascal, for your very, very informative presentation. Well, congratulations, really, especially the last model simulation was really insightful and made things really understandable, even for not exactly technical technical Sovi people like me. So it was very, very nice. We move on with the webinar now. Of course, I remember you that you always have the opportunity to drop any kind of curiosity or question to the speakers, but I leave the floor to Nicolas now that is fully set.
Okay,
Up to you.
perfect. Okay, you can see my screen. Is it okay?
It's wonderful. Perfect.
Okay, perfect. So, good afternoon, everybody. I will focus more on the technical part. Sorry, Francesco. So, I'm the technical director of the Iris iCar data center. So, I will just start for who we are. We are a data and services center that is situated in Lille, north of France. And historically, we are mostly dedicated to satellite data harvesting and processing, but we also have ground-based and model data in our database. You can see here the different kind of data we have and the different kind of visualization services we have developed. Regarding the infrastructure, we have 6.7 petabytes of usable storage capacity. We have 1,000 and 2,000 cores dedicated to systematic production, and we are routinely processing around 50 algorithms each day. We also have a very good bandwidth, and we have a 10 gigabyte bidirectional connection to the Renater network, which is a part of the French part of the Géant network, which is the European one. We are part of the data research infrastructure that have been presented in previous webinars, so I won't go further in description of the data era. So we are trying to build an interoperable infrastructure, and to focus more, you'll see the big picture here, to focus more on this use case. The idea is to get the data from the Sentinel 5P data hub, which is where the data are in Italy. The data are transferred and synchronized in Iris iCar in Lille here. The data are shared with the CNES, and the processing are operated at the CNES. After that, the data are made available for users everywhere, and more specifically, they will be made available to the European Science Cloud like EOSC. So you can see that the main part, I would say, of this processing is the data that are collected by iCar and the processing that are made by CNES. So why CNES and iCar? Because we are complementary. For this algorithm, Pascal presented them, we are at a bigger level that we had days ago, months and years ago. We have to process a big volume of data, of input data, with big computing resources. We, in the satellite data community, we were used to process very huge data, but with quite simple algorithm, quite simple in terms of computing resources, which is quite different from the HPC world, where there are need a lot of computing resources, but most of the time with less tiny input data. So the idea of this coupling is to use the best part of us, because the specificities of the CNES is to have access to important computing resources, and they are experts in HPC, and we are not, and they are also experts in data sharing techniques. Here at Iris iCar, we have access to a big satellite database. We are very close to the atmosphere science community, and we are close to labs, and we are experienced in science prototype industrialization and operations. So the idea is to mix the best part of these two infrastructures. So here is a big picture, very high level implementation scheme. I won't go into very specific technical details about that, but this is a general idea. So Pascal presented that. We have different ways to use the infrastructure. We have one part is the systematic processing of level 1 data. We also have the on-demand processing of level 2 Sentinel data. And of course, there also a need for data user to be able to get the resulting data. So the scheme is work this way. The data are collected each day from the ESA Sentinel data hub. It represents at this time, it represents 500 gigabytes per day. These data are retrieved and synchronized on our database here at ICAR. This database is shared with the CNS infrastructures. For the systematic processing, it works this way. So our computing services trigger processes on the CNS computing services. If the data are not, the input data are not cached on the CNS system, they will be retrieved and cached, and then the process will be triggered and the resulting data can be collected. The on-demand processing for well-identified and well-known users will work this way. So the user will trigger the process through a web portal and or web services. Same way, processing eventually the data can be cached on the CNS system. The processing will be triggered and operated, and the resulting data will be made available for the user that triggered the process. And of course, the last type of use case of users are the one that want to collect the data so there will be a catalog and a web portal where the users can interrogate and for the data discovery and get the resulting data so they can process them. And I'm good with that. This is my last slide. Thank you very much for your attention.
Thank you very much, Nicolas. I would like to pass the floor now to Dominique Jolivet from IGEOS. Thanks again. Congratulations to you, Nicolas, as well. You said that you were supposed to be very technical, and you've been, but I mean, have been particularly hit by the high implementation scheme slide. It was really understandable, and it was pretty nice. Systematic processing, the way you depicted, yeah, it was very digestible, and I think very, very much informative. Now I will leave the floor to Dominique to moving on with the rest of the webinar. Thank you.
Yeah, thanks a lot. Good afternoon, everybody. Here it's Dominique Jolivet from IGEOS. I will tell you a few words on the technical implementation of the algorithm and the processing line to exploit Sentinel-5 precursors to detect extreme and anomalous atmospheric events. First, I will give you a few words about our experience with Spatia in this field. We will be strongly inspired from the experience of the sensor EASY on board METOP. We had already principal component analysis processing of EASY level 1 data. It has been already tested and it's running It was a study with a Spatia IGO Centlatmos, a French academic laboratory with funding of the French Space Agency, the CNES. I will give you some example of this approach and the methodology and an overview of the promising results, but not an overview, only a few results. The second section will be dedicated to the ongoing work, that is the real implementation for Sentinel-5 precursor, with the generation of the reference basis, the data reader, and the principal component analysis. And we will finish with the challenge aspect relative to the Sentinel-5 precursor data and to the output that can be reliable for the end users. I will start with the processing scheme of the principal component analysis of the method we chose. That is the global workflow. Don't worry. In yellow, orange, you have the step of the processing. In blue, you have what you need before to start. To operate principal component analysis, you need a reference basis. You need the basis of eigenvalues. For that, you need to pick up a large number of spectra, that is about 100,000 spectra. You have to do this basis has to be representative of different state of the atmosphere, of different time in the season, different season. 1 year is enough. Different latitude, longitude. It should be very representative of a global set. For that, with this basis, we applied the principal component analysis and to calculate the covariance matrix. We get, that is in blue, is a step, the mean spectrum and the eigenvalue data set. And we have that, we will use that for each processing. So now we can go to the yellow steps. First, we read the data. Here it was the case for the EASY sensor. We get the radiance. From that, the radiance in the whole spectrum. We use the reference basis on the set of the eigenvalue to decompose the measured signal, and we project the measured signal to this base, and we get, that's step 3, the reconstructed radiance, as Pascal already talked in his first presentation. From that, we calculate the residual difference, that is the difference between the reconstructed radiance, the reconstructed spectrum, and the measured spectrum. If you have some outliers, like in this case, between step 4 and step 5, you can see a kind of peak. We can define that is an extreme or anomalous events, atmospheric events, and we map them on this graph. I will not enter in details into the equation and the mathematical aspect of this method. It's not the scope of this talk. So what I said also before there is that this method has been successfully applied to EASY and METOP. For EASY, we got more than 60 indicators or scores of extreme atmospheric events. It was concerning more than 10 gas or molecules like the monoxide carbon, the ammonia, the methane, the dioxide, sulfur dioxide. On the right, you can see an application. It's an animation on the months, on the August months of 2017, the whole months. You have on the top the CO and on the bottom the NH3, and that was where extreme events were found. You can see on the left of the map in North America, fires on the west coast, and the plume moving from east to west, and we can see some events in Siberia also, and in the north of Indian Himalayan area. So what I said, we need a reference basis. We need a set of eigenvalues to perform the processing. We can see that set of eigenvalues as an ancillary data. It has to be done once or maybe two if we make a separation between observation over land or observation over sea, for example. The reference basis is composed of more than 75,000 spectra. They are selected with a random-oriented method. It has to cover the long temporal period. Typically, it is 1 year. We choose 1 day every 5 days, so for the 12 months. And we pick up 75 spectra about per orbit. It's an orientated random selection, yes, because we want to have a representative set of skyline on ground pixels number. We want to have a representative variation of the solar on the viewing zenith angles, the solar, that is the sun position, on the position of the satellite. And we need a representative latitude, longitude set. As an example, for those who are interested by mathematics, on the left you have the covariance matrix, and on the right you have the value of the diagonal values of the covariance matrix as a function of the wave number or as a function of the wavelength, if you prefer. Now, talking about the implementation of this method for the Sentinel 5P L1B data. So it's you have an example on the right of data. It's for one skyline. You have the ground pixels on the y-axis and the spectral channel on the x-axis. It's what we have to read. So first we read the L1 level 1 data measurement. So the dimension is skyline per ground pixel per spectrum and the associated flags delivered in the level 1 data. For one ground pixel into a scanline, so for one spectrum, you have to detect and correct anomalous measurement. We have to filter them if necessary, so we will use or not, and we have to normalize it. And the output of this module is a temporary output, is the filtered normalized spectra. Note that I put in a pink 2 modules. These are very challenging for Sentinel 5 precursors, and I will go back after to this aspect. The second part of the algorithm is the principal component analysis itself. So the input are the filtered normalized spectra. We use the set of eigenvalue in blue, all in the same module. We project all spectrum, or one spectrum each after each, on the eigenvectors basis, and we generate the reconstruct spectra. After that, it's time to calculate indicators, to test on threshold indicators, and if we have a signal of alert, we give outputs. Indicators, just a few words of the indicators. The residual radiance is the difference between the reconstructed spectrum and the measured spectrum. This value is calculated for different spectral range. So whole spectral range, band 7 or band 8 in the shortwave infrared for Sentinel-5, or its dedicated spectral window for each molecules or gaseous species. And as an indicator, mainly we use the mean of this value, of the standard deviation of this value. So now a few words on the challenging aspect of implement this algorithm with Sentinel-5 precursor data. Just to say that the code is written in Python with GoAPI Python. The processing is done at the scale of an orbit. So it is divided into chunks, it's arrays of data. Difference between Sentinel-5 and EASY is that we have much more input data, but only 3 bands for Sentinel-5, and we only use daytime observation. A few words about the modules in pink I showed you previously. So it's the difference between also Sentinel-5P and EASY. For Sentinel-5P data, we have to deal with noise. The noise is radiance dependence and sense dependence. So it's very different from EASY. We have to normalize the spectrum. So the instrument covariance matrix has to be established. It's more complicated than for EASY. We have to define a spectral indicator in the shortwave infrared. It has to be defined as for EASY by searching for the most appropriate spectral signature, for example, of methane. It will be the first priority to focus on the CH4. On the carbon monoxide, that's the second priority, since it's also spectroscopically strongly perturbed by methane features. Water vapor features are also to be considered because of their ubiquity and the large variability on a temporal and spatial scale. And also other species will be searched for in is a discovery or extreme event mode that will be during the prototype. And we have to take care also of the day-night transition, since the recorded or measured signal is a solar radiation reflected by the surface atmosphere system. So low sun sands will be filtered out. We will apply a threshold for high solar zenith angles. It's a double advantage, because for high solar zenith angles, we cannot consider that the Earth's atmosphere system is not plane parallel anymore. So there is a lot of effect of large air mass to be covered and to be traveled. It means that if you have a very grazing zenith angles, you don't see, when you look at pixel, we don't see a small part of the of area, but we see a long horizontal distance. So it's very hard to map and to interpret such results. Finally, with Sentinel 5P, we will have a huge amount of input data. Does it mean that we'll have a huge amount of output data? We hope not, because we will only detect extreme and anomalous atmospheric event. A few words about the output, because it's also challenging. The main output will be a logbook of atmospheric events detected in an HPDA file. The question is how to be efficient and useful for users and researchers. So people want to know if there is an extreme event, what it is, and how to find more information on it. So we have to know where is the level 1B data. So we will give as an attribute the file name. We have to know how in this file name to find the measurement. So we'll give the scanline, the ground pixel number. We will also associate the ground pixel quality flag that comes from the level 1 data. We'll give the spatial geolocation, that is latitude and longitude. We'll give which indicators that provide an alert that can be methane, monoxide carbon, LH3, etc. So we will create a detection flag coded in 8 or 6 bytes, depending on the number of indicators. And we will give the value of the indicators, the mean and the standard deviation of the residual difference. We can also investigate some other outputs. It can be investigated and validated by IRIS ICAR, I want to say, that is maps of the extreme event. That is post-processing for the whole day, so the 15 orbits covering one single day, and maybe to develop tools to link to level 1 data and to level 2 data corresponding to detected events. I want to add, we want to add an additional difficulties, that is that bad pixels are always present in the SWIR shortwave infrared focal arrays. So we need to establish the map of bad pixels in the spatial, so that is the ground pixels, so the instantaneous field of view on spectral, that is the channel plane, using solar calibration views, that is performed once a day on board Sentinel 5P with a diffuser plate, and that is acquired when we just look at the pole and we can look at the sun. So it's with this challenging aspect I finish this talk. Thank you, merci and grazie mille, and I think it's time to give the floor to Xavier.
Thank you very much, Dominic. Very to the point, very well detailed presentation. So we have now completed the 3 presentations dedicated to PHIDIAS. I think hopefully you have now a better understanding on how PHIDIAS use cases. One is making a good usage of HPC data management for the development of intelligent screening approaches. I will now pass the floor to Xavier. Xavier is our guest of honor in this webinar. He's speaking on behalf of ESCAPE, the European Science Cluster of Astronomy and Particle, that's a necessary research infrastructure. And I would like to say that we are all very glad to have Xavier in here. And as you know, ESCAPE is a project dedicated to the EOSC implementation. It's a cause that PHIDIAS is equally committed to. So we're very glad to have you in here, Xavier, and leave the floor to you now. Thank you.
Thanks a lot, Francesco, and thanks a lot for the invitation. It's been a real pleasure. I would also like to thank all the presentations, because like this, I got a very nice overview of the PHIDIAS project, and it was quite interesting. And also this allowed me to basically steer a bit my presentation towards what I can see that it can be helpful and more interesting for you. So let's go straight to the topic. So I would like to describe very briefly what is ESCAPE and what we are trying to do in ESCAPE. So the main goal is to prototype an infrastructure which is adapted to the very large storage needs of upcoming large science projects like high luminosity LHC at CERN, the square kilometer array, LSST, CTA. So this is in the framework of cosmology, radio astronomy, and particle physics. We are talking about experiments that will be producing at the level of exabyte data per year. This means 1,000 petabytes per year. So this is huge. And on top, the sites which are providing resources, not only storage, but compute, are sometimes sharing this infrastructure across all of these experiments. So a common data infrastructure is something that I really would like to pursue, and this is what we are trying to do. On another perspective, I think ESCAPE is an important player because it will ensure that the science drives the development of the European Open Science Cloud. It's important that science is there. And of course, what need to follow is to address the fair data management principles that should grant to the user and to the scientist the fair amount of data management tools and access to data. So what is ESCAPE, and more in particular, what is this data infrastructure for open science? What is a data lake? So what we are trying to do, I would like to describe this picture, which can seem a bit confusing, but let's follow my fat cursor here. So in this upper part, what I wanted to plot is that the sites that are providing large-scale storage, or federation of sites providing large-scale storage, hundreds of petabytes, I would say hundreds of thousands of CPUs. This is the typical site we have as a high-level computing center for particle physics, for the LHC and several experiments. So these sites are the ones that really has the expertise to run large storage systems. I mean, 100 million of files in the namespace, 100,000 of disks. So they really have the expertise, but they work right now kind of in an isolated way. So what we are trying to do is to put a kind of data management system on top of that to harness all of these sites and the data which is there to do a kind of a global federation of the storage, which we call a data lake. Our understanding of data lake might be different from the academical definition of a data lake, but this is basically the name that we give. So in this way, at this level, we can have a overall system where we can apply quotas, we can apply access control lists, replication rules, and we can enable some new concepts that will allow also to run in a better economy of scale and increase the optimization of the total cost of ownership of hardware resources. I'm talking about storage quality of service, which basically, now at the computing centers, there is the tendency to run the hardware towards the end of the lifetime, so that is performed quite well. So imagine the experiments at the beginning, they inject data to a kind of storage which is very reliable, very fast, but after a few weeks after processing, they want to transition to something which is more temporal, and eventually this data can transition to tape for archive, and you basically read it after several years or never again. So setting this quality of service across the data lake, across all the sites, will allow us to have the implementation of data lifecycle from the experiments implemented at the time to inject data. So we don't have data which is parked, which is occupying a space in a precious disk, while it can be sitting happily in a tape. And this, like this, we can basically increase the improvement of the total cost. So okay, so this is the higher part is where the data resides. So we have a data management system. We have means to transfer data from one side to another, doing it in a systematic way, checking the data corruption, a single identity management. But I think it's more important probably for this webinar is how to connect these switch computing resources. I understand that this bottom right part, these boxes, I put here the HPC centers, remotely operated sites, or commercial clouds. These are entities that could benefit from this data and can be opportunistic or which are not the classical sites that we know it in the whole LHC computing grid. So what we see here is that there is usually in the HPC centers the need. The difficulty is to make the data ingress and data egress, how to pass data, big data volumes to HPC centers. We put 1 petabyte, you process it, and then you spit out the outputs. But how you do this? So we are thinking about ways to basically easy this process, because HPC centers can be quite demanding on the security, the way to pass the software, how the network is provided. You know, it's not easy sometimes to start working with them. So in this next slide, I would like to show that a bit more in detail these storage sites and how is the Escape Data Lake now organized. So it is the places where the experiments inject the data. You see that I mentioned in the beginning there are several sites, big centers like Lyon, CC. We have DESI in Germany, INF in Italy. So across Europe, we have many sites which basically run storage services which are federated with these tools as a high level. So in some sort of sense, this data lake is, the complexity is hidden from the user, is hidden from the experiments. And basically, this is basically a big pot where to put the data and where you find it afterwards. So I was basically starting the discussion about how to join with HPC Center, and it's basically my next slide. And I would like to give a word, to say a word about content delivery and caching. So in the last year, we are of course investing quite a lot of time in the LHC future computing to find ways to lower the cost of storage, because I mean the challenge we have in 5-6 years is enormous. So we are investing quite a lot in demonstrating or showing or investigate how a cache can work. And in fact, these streaming caches could work quite well on a data lake environment. And streaming cache is a simple stateless storage service. Say a disk server, couple of disks, can be virtual volumes that basically start to receive data when the job starts to process at the site, at the HPC or at the commercial cloud. It works like a kind of not exactly, but in a YouTube fashion, you start reading the file, you start processing, but the file is getting consolidated in the background. So the next events are really fetched from the local site. So like this, you can really hide latency in case the latency is high to the real source of the data. So we are investigating right now in Escape whether this caching mechanism can be also good for non-event based formats. In particle physics, we have events, we go event by event basically. But in radio astronomy and cosmology, there is also the component of image, videos, or data cubes. So the type of input data is different. So we are doing tests about how the cache can work on that. I would say is interesting to emphasize that these caches can facilitate quite a lot the ingress and the egress of the data with HPCs. These are services, storage services that can live in the barrier, in the frontier of the HPC and the outside, and you can have quite fine-tuned control of the access, the ports opening, and etc. So here there is a sketch of how this works in the latency hiding purpose, and also in the file caching. And the pure file caching, this means that once the file is in the cache, you can repeatedly access basically locally. So on the top part is the application running in commercial cloud resource, HPCs or sites. Then there is this caching layer which interact with the data lake. It is basically the high level overview. So what we are doing in Escape right now, so we are at the basically 1.5 years of the project. We have strong engagement from several communities. We have radio astronomy experiments. This is the LOFER and SKA communities. We have astroparticle through the CTA and MAGIC telescopes, which are sitting in La Palma. We have the cosmology with the Large Synaptic Telescope. We have also representation from gravitational wave, this EGO-Virgo collaboration, and of course, particle physics in the nuclear physics side, which is FAIR, which is in the GSI accelerator, and then ATLAS and CMS in the LHC. So just to show very quickly that these experiments are starting in ingesting data in the data lake, and some of them even are reproducing analysis. I would like to shortly show this demonstrator that was basically presented, I think it was about a month ago, where the ATLAS people managed to reproduce a Nobel Prize win analysis, which is the discovery of the Higgs. This was run on a Kubernetes cluster running a Jupyter notebook, and then getting the data from the data lake in Escape. We have right now the ability to produce. So we produce a module, which is a Jupyter Lab extension that can run on a vanilla Jupyter Lab implementation that can interact with our data management system. So the users can look for data, can download data, can process data, and even can make use of a cache just by using this standard Jupyter Lab implementation. This is something we are really pushing the throttle right now. So, and where we are pushing the throttle. So right now we are in here, I put this red circle in November 2020. We are preparing the data lake performance analysis, and really we are up to speed because we want to test many things. So the experiment, the project started in February 2019. We are right now 1.5 years roughly after the start, and we have a bit more than 1 year to go. But really, I think that the challenge we have, we are investing time at the moment, and started to be very interesting. So what is this data lake performance analysis, and what is the challenge? So this is what we want to do. This is for next month. What we want to do is an assessment of the pilot data lake. So we have a pilot data lake with 10 sites, composed by 5 storage technologies in different sites. We are allowing 3 protocols to interact with the data lake. We have these 4 of this storage quality of service, which is one fast for analysis, which will be relying on SSDs, one for archive that will be relying on tapes, one of opportunistic processing, which will be relying on obsolete hardware with a single copy. This means data you can lose or is replicated elsewhere. And we have a single authentication mechanism. So what we want to do is to really do a full rehearsal of this initial implementation of the data lake on a single day. So we really want to test from data injection from the experiments to data replication across the sites and the data lake, and test the data access. So this will give the perspective from 3 different views: from the scientists that will be exercising the lake, from the sites that will be operating the services, and the assessment of the data lake tools and service. All of these orchestration mechanisms that I mentioned: data management, file transfer, authentication, information system, etc. So the first exercise will be the 24th of November. After this, we will have a workshop to assess the performance and to prepare a second one before the end of the year. So we have 9 experiments involved that will be injecting data and implementing data lifecycles test. We will test in an easy way data corruptions to see how the system reacts for data corruption. And we have, of course, monitoring testing. We have now quite a lot of graphics which shows the in-flight transfers, the network throughput, number of files, storage services, etc. And at the bottom, and the most important, is basically the data access. So how the people can interact with this data in this pilot phase. So this will happen very soon. And this is our main focus now. And of course, as you can see, we are not closing the door to anyone which is outside the project to join, because I mean, we have even people from Australia that belongs to SKA, which are participating in the project. even if they are not part of the project. So this is something that is a data lake for open science. Anyone that could be interested in testing it, we are happy to turn bridges to welcome anyone. So this is an invitation for all of you if you think this could be interesting. So I would like to really flash this transparency, which I took yesterday, some snapshots randomly from our monitoring. You see there are matrix, which basically shows transfer from one side to another. There are some reds, which are we are still sorting out some things, just to see that there is some activity. I will probably put a live demo next time, but right now the access is a bit restricted. So basically that's all from my side. Thanks for listening, and I will be happy to take questions if any. Thanks a lot.
Thank you very, very much, Xavier, for your very nice presentation. Yes, I think I would like to pass the floor back again to my colleague Pascal, because I think he wanted to point out few aspects of his presentation, but at the same time, I think we have a question from the audience that came in right now privately. That probably Pascal, you're the better one to reply to. They're asking how these PHIDIAS use cases, yours one, I mean, is going to be supportive for the end users community. In which perspective? I mean.
Okay. Thank you, Francesco. First of all, I would like to thank all the speakers, of course. Just to address that question, hopefully the idea is really to be in position to first deal with scientists, which are probably not the end users as you can imagine them, but we have to deal with them in order to verify and control how this processing, specific processing, is powerful and useful. But from that, we hope that the way of that processing to focus on data of interest will open the door for end user to be able to benefit from specific services. For example, we hope that from atmosphere, we would be able, with space data, to detect some industrial disease, industrial accident, something like that. And we would be able, together with a service provider, to give that information in some way to end users, such as industry, etc. But of course, these have to be built together. So we will see. The idea is really to put, as you perfectly understand, PHIDIAS' goal is really a tentative to merge expertise on HPC, high performance computing, high storage, together with thematic use of space-based and also in situ data in order to make something which is meaningful and which is powerful. This is really our goal. And the other point which is very important is to do that together with users by putting all the information available before the end of the project and exchanging with users as they want. So this is a goal. Another important goal of that project is also to use the capabilities of HPC to work on inter-thematic or multi-thematic issues. As you understood, this is not the object of the present webinar, but there is also work on ocean and land data. And one hope of PHIDIAS is really to deal together with the data and, for example, give the opportunity to atmospheric users to also use information from land surface, etc. So this is also very challenging, but this is the goal of our work, and this is why there is a lot of connection between the use cases. And finally, coming back to the atmospheric case, I would like to insist on the fact that with the processing we are developed, we would be able to have some ready-to-use processing both for infrared atmospheric sounders and more UVVs, near infrared atmospheric sampler, that is all the spectrum of atmospheric sampling. And this is very important to have that available for the next generation. As we said, there will be a lot of data available from all that spectral domains. There is challenge to merge and to put synergy between, for example, Sentinel-5 and NG on METOP-NG. This, we hope that PHIDIAS could help also to do that. So there is a lot of challenge. We hope that this PHIDIAS project will allow all the users, all the experts, and all the scientists to work together on data.
So Pascal, thank you really very, very much for your clarification, for providing us with as additional and very useful information. So since we're running a bit out of time, before quickly wrapping up this event, I would like to give you just a couple of tips. As I reminded you in the chat, by tomorrow you will be able to find both the video and the slides of this webinar on PHIDIAS website. So feel free to get there, and yeah, you can even dig deeper and maybe go over things you would like to better understand. This webinar, of course, is not going to be the last we are running. Around December, hopefully, or at latest in January, we will conclude the use cases series with a big data Earth observation webinar. And in this regard, I would like to invite you to follow us both on Twitter and LinkedIn, so you will be entirely sure to be completely abreast of our happenings and whatever is happening, not just webinar related, but whether we're going to participate to external events or any kind of opportunity. So I'm going to wrap up and close in here. I would like to thank you very much again for staying with us today, and the speakers for their remarkable work, and all of you from the audience. I've been particularly impressed by the fact that the vast majority of you stayed with us until the end. So I'm pretty sure this webinar has been helpful, has been engaging, and very active as well. So even on my side, I wish you a very good day, and stay tuned to PHIDIAS. We will catch up in the next weeks. Thank you again. Goodbye.